Welcome back to this advanced manufacturing and process modeling course. So, we were discussing powder metallurgy module of the course, and we have also discussed already about different powder preparation and processing techniques. So, today we will finish this powder metallurgy module. So, we will discuss about how to design the runners ingates to develop a appropriate mold cavity, so that we can get desired part quality and also with the desired dimensions of the green compact in case of injection molding, because it is the key to achieve the desired dimensional attributes and density attributes in the green compact state, so that we can achieve the desired mechanical and physical properties in the sintered state. So, let us start with this critical summary of runner systems in injection molding. So, runner as the name implies is like we have discussed earlier also in case of casting solidification. So, it is basically the geometry which carries the this polymer or liquid metal polymer mixture in case of metal injection molding, or ceramic polymer mixture in case of ceramic injection molding. So, it transports that melt from the injection barrel to the mold cavity. Its design, configuration, dimensions and connection with the molded part directly impacts mold filling and product quality. So, below is the categorized summary of different runner systems. So, key components of a runner system is sprue bushing. So, it receives molten metal from the injection nozzle and feeds it into the runner system. So, for example, it will be sometimes look like that. So, so this is maybe the runner, and then from here it will get distributed, channelized, and then it can go to the component cavity. So, this is so here so you can say that all these things these are runner. So, these are basically the connection between the sprue base or you can say the sprue bushing and the the component cavity. So, this is component 1 and this is component 2. So, these runners are responsible for connecting with the component from the sprue base. Okay. So, so runners distribute molten plastic or melt into the mold cavity, especially in multi cavity molds, and gates are the narrow cross sections areas that ensure easy and clean separation. So, basically these are the regions which are called gate. So, these are the region where from we can see that these are the locations through which the plastic polymer melt or polymer metal or polymer ceramic mixture enters into the component cavity, and they are also responsible for ease of separation of the component post molding from the this component tree. So, also it aids in fully automated operations and optimizing melt transfer to cavities at desired locations. So, types of runner systems: standard runner system, runners are machined directly into mold plates at the parting line. So, melt remaining in the runner freezes and is removed with each shot, and advantages are recyclable frozen material for thermoplastics, and disadvantages like for thermosets material is unrecoverable, leading to waste. So, this is the key takeaway. So, you can have the luxury to design the runner, even a little over design it in case of thermoplastic, because you can reuse the feedstock material in case of MIM or CIM, and plastic material in case of polymer injection molding. However, that is not the case in case of thermosetting polymers when you are dealing with the injection molding of thermosetting polymers, because they are not reusable. So, that means the solidified material in the runner so that they become say waste. So, that is what is the remedy to that? The remedy can be to implement hot runner systems, that we will be discussing next. So, hot runner systems is the functions as an extended injection nozzle with heat barriers isolating it from the cold mold. And so, basically in case of hot runner systems, the melt it never solidifies, it remains always at fluid state, and through this hot runner system it enters into the component cavity capacity. So, you can understand that it basically significantly reduces the waste generation, because I mean the runner geometry remains always fluid and it is only the component cavity gets filled. However, it poses certain complexity into the design of the runner systems, and that is also a disadvantage, because it significantly increases the cost of the mold, and I mean so risk of decomposition and low thermal resistant materials is prone. So, that because it is exposed to the heat for a longer period of time. So, however, this is an effective technique or effective approach for thermosetting polymers, where you cannot reuse the I mean polymer which is solidified at the I mean runner system. So, hence it is useful, and whereas cold runner systems are like the runner systems, where the material basically like I have drawn in the last slide and explained to you. So, it is basically connects the sprue base well with the I mean ingate of the I mean mold I mean component cavity, and they are generally I mean in case of polymer injection molding, it is the thermo I mean plastic polymers that is used, and also in case of MIM and CIM also I mean thermoplastic polymers are generally used as binder materials. Hence, the feedstock material which is solidified I mean the polymer part has solidified in the runner, they can be reused by remelting the binder component. So, however, there are disadvantages for cold runner systems as well, such as high pressure consumption increases design complexity and cost, and uneven viscosity due to slight temperature differences results in non-uniformity non-uniform cavity filling. So, another important thing that is not I mean mentioned here, that is powder binder separation. So, that is also a key problem when this happens when we are dealing with. So, this is a intrinsic thing for CIM and MIM. So, because as we have already discussed that in this both the processes we basically load the metal and ceramic powders with the polymeric additives, and they basically facilitates flowability of this I mean metal or ceramic powders. So, hence in these processes because of the drag and the difference in viscosity, there is a tendency for the powder accumulation in some regions within the component cavity, where some other regions there is a chances of accumulation of the I mean lesser viscosity polymeric ingredient. So, that needs to be avoided. I mean that can be done by effective design of the runner systems. So, now the sprue. So, sprue is the part which is taking basically the melt from the injection nozzle, and then it is distributing into the I mean component I mean getting geometry. So, I mean it basically it releases the melt into the runner systems, and in cases where it is a I mean sprue based getting system, then it directly releases it to the component cavity. So, that I mean so therefore, I mean runner systems, to offer the optimum quality and economics to the user, the sprue design has to be effective. So, I mean so the principles are the runner which remain with the molded part and therefore be cut off afterwards, runner which are automatically separated from the molded part and are demolded separately, runners which are automatically separated from the molded part during demolding, but remains in the mold. So, these are basically different kind of runner systems that the sprue connects to, and the wear resistance. So, hence the mold need to be made of hardened steel, because as we have talked about I mean MIM and CIM also. So, then I mean specifically in case of CIM, the ceramic particles are very I mean generally in hard very hard in nature, and they simply causes I mean abrasion with the mold walls, and which results in enlarging the cavity a bit. So, how to stop that? To stop that, it is I mean it can be done by I mean the mold cavity can be developed by hardened steel, so that wear resistance can be improved, and then the flexural fatigue strength. So, therefore, a strong but not too large flange and rounded edges that can be implemented, and since the sprue always leaves a mark on the molded part, is as small a diameter as possible can be kept However, I mean one thing you have to notice here, that in case of casting, if you recall that we have discussed about the sprue, which is a converging cylinder, but this is in case of casting. This is a basic difference with casting and injection molding, whereas in case of injection molding we are talking about the sprue design, which is basically a reverse taper. So, why is that? Because in case of casting, our goal is to basically increase the velocity, and that thereby the pressure is also dropped. The goal is to have a full flow, so that there is no air aspiration happens. But in this case, because already the melt is getting injected with the help of pressure by the plunger or by the screw based machines. So, in case of up to the sprue base well, which is this is the location, the velocity is also dropped because of the enlargement of the cross sectional area. Although there are differences, differences can be found in case of sprue gating system, that we will discuss. Okay. Yeah. So, sprue gate. So, this is a typical example of sprue gate, when you can see the sprue is directly releasing the melt into the component cavity, and there is no runner systems present in this case. So, you can see the this negative taper in this case, where it is showing a diverging geometry. So, in the applications are temperature sensitive and high viscosity materials, heavy and high quality parts. Advantages are high quality parts with precise dimensions. Disadvantages, it requires post processing for sprue removal, visible gate marks. Okay. And then the case of edge gate. So, edge gate is a typical example is shown over here. So, you can see the gate is just from the sprue base, there is an extension to enter into the component cavity. So, in this case, of course, the runner is present, and there is the ingate is kept at the edge of the component cavity, or the so the applications are large area parts like plates and strips. Advantages are no neat lines, high dimensional accuracy that can be achieved, and disadvantages like post operation for gate removal is needed. And then another interesting gating type is disc gate. So, it is useful for axisymmetric parts with a core mounted on one side. So, you can see that it is basically connecting in the form of a disc to the component cavity. So, this is advantages are no neat lines, no strength reduction, and the disadvantages is post operation for gate removal is needed in case of disc gating arrangement. And then the case of ring gate. So, you can see from here that it is basically a throughout annular throughout the circumference of a cylindrical part, the gate is connected. So, it ensures a uniform filling of the component cavity, so that it can it ensures that filling of the all the locations at one go, at simultaneous speed and also at simultaneous time. If it is a multi cavity mold, this also ensures that all the component cavity receives the melt at the same point of time at a comparable speed. So that there is no difference in the morphology and properties. Applications are sleeve like parts with cores mounted on both sides. Advantages, uniform wall thickness around the circumference, and the disadvantage are slight neat lines and post operation is required in case of ring gate. Okay. So, moving further, now we will discuss about the tunnel gate. So, you can see this configuration and you can understand the name implies from here itself. So, it is basically getting connected into the mold cavity a slide below from the parting line, and hence it is termed as submarine gate or tunnel gate. So, the applications are smaller parts in multi cavity molds and elastic materials. Advantages are automatic gate removal, because you can from the geometry itself you can understand that the gate ingate becomes very fragile after solidification of the component. So, hence it gets removed while ejection of the part from the component cavity. So, it gets automatically the junction gets broken. And and then the disadvantages are high pressure loss limits its use to simple parts. So, so pinpoint gate like it is useful for a 3 cavity mold. 3 cavity molds are such where there is a one half is typically kept for the to house the component geometry, and then another hub is basically kept to take the melt inlet, that means the sprue bushing. So, it is that is what you can see from here. So, this is one parting line, this is another parting line 2, and the in the buffer cavity which is between the in between of both the mold hubs, that hub contains the runner and the in-gate geometry. So, this is how it is possible to be arranged. So in case of 3 plate mold pinpoint gate, applications are multi cavity molds with center gating arrangement. So, that is what is shown here, center gating, and advantages are automatic gate removal. Disadvantages, it produces a large volume of scrap, molds are costlier. So, these 3 part molds are only useful for very complicated components, complicated micro components, where there are multiple the cores, and also the these cams are needed to move the ejection mechanism. So, in that case it is not possible to house the entire system effectively in only 2 die hubs. So, that is why another die hub is generally introduced. Okay. And then pinpoint gate with reverse sprue. So, this is a typical example of a reverse sprue. In this case you can see the geometry is quite similar with the what we have discussed in case of casting solidification. That means it shows a converging sprue type. Applications are automatic gate removal for thermally stable materials like polyethylene and polystyrene. Advantages, no post operation. Disadvantages, limited use for materials other than PE and PS. This is because of the significant increase at the velocity at the entry to the mold cavity, component cavity. Likewise, that is why in case of injection molding, we always use the sprue which are act like a diverging cylinder. But so, this is a special case applied for polyethylene and polystyrene, where that higher velocity does not cause much trouble. It basically useful to make the molding at a faster rate, and also it does not allow to create defects due to turbulence, and also hence it can be applied in this case. And then there is hot manifold gate. So, applications are high quality technical parts suitable for materials difficult to process. So, the advantages is no material loss from the runner system, automatic gate separation in this case, and disadvantage is expensive molds due to advanced control equipment. Okay. So, then we continue with the discussion of the in-gate geometry. So, so in case of circular cross section, so it involves minimal surface area to cross section, relative to cross section. It facilitates slower cooling rate, reduced heat and frictional losses, and center of channel freezes last, ensuring effective holding pressure. So, this is true for in case of the runner geometries also. It requires machining into both mold halves, making it expensive and complex. And then if we are talking about parabolic cross section, so in case of parabolic cross section, approximates a circular cross section for optimal flow, easier machining, because it can be, in this case the the runner geometry can be developed in only one half of the die cavity, one of the die halves. So, easier machining, usually the movable side for ejection it is kept. And the disadvantages, so the disadvantages are higher heat losses and more scrap compared to circular cross sections. And then the trapezoidal cross section, so which is again a approximation of this parabolic cross section, that is shown over here. So, in this case the advantages are it serves as an alternative to the parabolic shape, and disadvantages are greater heat losses and scrap generation than parabolic shapes. So, this is the in case of trapezoidal cross section. Followed by that, there are some unfavorable cross sections like flat or rectangular cross section are highly discouraged due to poor flow characteristics. And also this geometry of like half circle, in that case also high heat losses takes place. So, hence these two type of runner geometry and in-gate geometry are cross section of the runner or in-gate are termed as unfavorable cross sections. And so, these are the 3 cross sections that we have discussed about are termed as favorable cross section for runner and in-gate geometry. Okay. So, then equation for loss of pressure in gates and runners. So here in this table it is the expressions are given. So, these are the equations for calculating the pressure drop as a function of length as well as the shear rates for various geometries of the intended runner and gate, both for Newtonian and pseudoplastic material behavior. So, these relations are based on the following suppositions. So, so the assumptions are isothermal flow. So, all flowing mass particles at the same temperature, stationary flow, no temporal change in flow profile, laminar flow, that means Reynolds number below 2100, it is incompressible, that means the density is constant. I mean throughout the space, I mean throughout the fluid body domain, density is remaining constant, and then no allowance for flow in and flow out effects, and then wall adhesion. So, I mean these are the considerations, and these are the typical expressions. So, in case of considering Newtonian viscosity, that is tau is equal to mu du dy or eta du dy. So, this is the shear rate, this is the shear stress, and this is the viscosity. So, in case of circular geometry, the pressure drop expression becomes like this: delta p by L is equal to 8 eta viscosity into V by pi r to the power 4, and these are the expressions for intrinsic viscosity. So, these are the equations that you may be necessary, you may be asked this kind of problems for designing the gates and runner geometry. So, hence it is recommended to go through this. And then here is a simple problem that is shown over here. So, here you can assume that these are the two molded parts, component 1 and component 2, and this is basically the runner geometry. So, this is ingot number 2, ingot number 1, and then it is basically the runner geometry from which it is getting transported to the component cavity. So, so let us assume that the simple hot runner system, that means the runner is always full with liquid and it is heated, hence it is only the component that gets solidified and not the runner. Adapted, so here the gate diameter dg2 of part 2 is to be adapted in such that the two parts are filled under the same conditions, that means simultaneous entry by the melt into the mold halves, end of flow paths reach simultaneously. So, you can understand from here, because this is basically the flow direction. So, hence there will be always a tendency of the flowing melt, either it is polymer or it is a metal ceramic, metal polymer or ceramic polymer mixture in case of MIM or CIM, whatever the case may be, to enter the first component earlier and then the second component. So, in this case the basic objective of going for multi cavity mold is defeated. Because in case of multi cavity mold, it is expected that all the component cavities, the melt, the polymer or the polymer metal, polymer ceramic mixture will enter simultaneously. So, to achieve that, we need to design the ingot and runner dimensions effectively. So, let us see how we can do that. So hence simultaneous entry by the melt into the mold hubs, end of flow paths reached simultaneously. So, the material to be used is characterized by the following data. So, power law, consistency factor K is equal to 1.14 into 10 to the power 4. And then flow exponents are small n is equal to 0.6. So, it is the relationship between viscosity and shear rate. So, it is eta is equal to K A T into gamma to the power n minus 1. So, we have already given the value for K, and then now, so as we have seen the tables which are given over here. So, this is the expression, earlier we have seen the expression for pressure drop delta P across the flow length. Here the expressions for shear rate. So, we will consider, so these are the expressions relevant to circular, annular aperture, rectangular and irregular cross section. So, in this case we are talking about a circular geometry. So, we will of course consider the first equation over here. So, so let us assume that the simple hot runner system shown in figure has to be designed as we shown. So, the material to be used is characterized by this following data. So, the dimensions of the hot runner system. So, hot runner as far as molded part 2, that means part 2 So this is the component 2 we are talking about C2. So in this case, so the LHR2 is equal to 50 mm, DHR is equal to 10 mm and LG2 is equal to 5 mm and DG2 is what? That is what we need to calculate. That means the in-gate diameter in case of component 2, cavity 2. So the hot runner system in case of component 1, LHR1 is equal to 120 mm, DHR. So these are basically marked over here, you can see. So here this is 50, 120. So from here you can understand. So that is why 50 plus 70 it becomes 120, and in case of here you can see it is 50 only. So from here the distance is 120. So hence, and then DHR is equal to 10, that is diameter of the runner is 10 mm on both the cases, and also the length LG1 and LG2 are same, that is 5 mm. DG1 we know, that means diameter of the in-gate diameter in case of component 1, that is this one is DG1, that is 3 mm. So this is DG1 and this is DG2. Okay. Hence, so this is we have to evaluate DG2. So for simultaneous filling of the parts, the pressure on both flow paths must be equal. So then if you equate delta P1 is with the delta P2, and then based on the pressure drop expressions that are available in the previous slides we have discussed. So then the expression becomes like this. So viscosity eta HR into LHR1 by d viscosity it remains constant. So hence we are considering it as constant eta HR for the hot runner system into LHR1 by dHR to the power 4 plus eta G1 LG1 by dG1 to the power 4 eta HR. So this is the expression. So after this, so because for the various viscosities the following expression applies. So eta is equal to k AT into gamma to the power n minus 1. Please recall, this is the expression for viscosity that we have defined at the very beginning. So this is what now we are applying to calculate. So given the representative shear force is equal to gamma I dot is equal to E0 into 32 V by 2 di cube. Again this is from the expression that we have shown in the table. So we can evaluate, we can, so these are the expressions need to be utilized based on the cross section of the runner and the in-gate, the particular pressure drop expression and particular shear rate expression, and then finally we can calculate the viscosity value like this, where we have putting the value of gamma expression for shear rate we are putting over this. So this equation is used here, and then finally the resultant expression is this, and then so the gate diameter calculation. So DG2 is equal to 2.61 mm, that is what is coming. So derived to balance greater resistance in grade 2. So you can see that the, so it is the flow is more constricted in case of component 2. Why is it so? So that you can quite easily understand from the geometry itself, because component 2 is nearby to the from the entry of the liquid melt, hence it is the diameter is kept lesser. So that is why DG2 is less than DG1. So hence the flow resistance to flow is kept greater in case of component 2, so that the simultaneous filling can be achieved for both the component cavity. Okay. So the pressure loss formulas. So formulas developed so far: straight channels, cross section transitions and turnarounds, and trial mold usage. So trial molds are used to determine material constants. So the labor intensive but beneficial for rarely changing molding compounds. So this is the expression for delta P, and then the evaluation of the rest test results with the help of equation can be presented in a double logarithmic system of coordinates, and then R becomes like this: delta P A by VFCL from this expression. So where R is the resistance to flow specific to the material, Vf is the medium flow velocity of the cross section, C is the circumference of the flow channel, L is the length of the flow channel, and A is the cross sectional area of the flow channel. Okay. So the mathematical relations for different geometric shapes are again summarized in this table. For straight channel, for elbows and for cross sectional transitions, the pressure drop is summarized over here. Okay. So now we will discuss about the individual gating systems in little bit more detail. So, in case of sprue gate, the sprue gate is a simple circular and slightly tapered gate. So, I mean which merging into the molded part at its thickest section. So, as we have discussed already that sprue gate there is no runner, it is directly allowing the melt into the mold component cavity. So, and it is allowing to do so in the thickest section. So, so in this case, so this is basically the geometry of the sprue gate. So, here the gate is directly connected into the component and it is getting connected into the thickest cross section of the component cavity. So, so this is so likewise. So, hence so the proper sizing ensures effective holding pressure during solidification, compensation for volume contraction during cooling, prevention of voids or sink marks. So, the key guidelines, the sprue diameter df should exceed the section thickness of the molded part by 1 mm. So, df greater than equal to S max plus 1 mm. So, excessive thickness prolongs cooling and delays solidification. So, tapering towards the nozzles prevents demolding issues. So, this is another reason. So, because it should be a tight fit. So, basically the sprue here it is taking from the nozzle entry. So, this is basically the nozzle and this is the sprue inlet from where the melt is entering from the nozzle to the sprue and thereby from the sprue to the getting geometry to the component cavity. So, so here the sprue inlet diameter should always be slightly higher than the diameter of the nozzle. Say diameter of the nozzle is defined as dn. So, then and diameter of the sprue is defined by ds, then it should always be greater than the nozzle diameter. So, that the entire melt is going into the sprue inlet diameter. So, so the excess so that the thumb rule is the nozzle orifice diameter must exceed the corresponding nozzle diameter dd by 1.5 mm. So, that means it should be at least greater than the the sprue inlet diameter should be at least greater than the nozzle entry diameter by at 1.5 mm. So, that is the thumb rule. Okay. So, so this is how we can achieve successful filling of the melt from the injection nozzle to the sprue inlet without causing leakage. So, that is what is recommended, and then in case of disc gate as we have already discussed the functionality, it ensures uniform filling of the entire cross section of cylindrical or sleeve like moldings and used when the core needs to be mounted at both ends, and the design type is plain circular shaped ones or conical shaped ones with a 90-degree taper. So, the advantages are it distributes melt uniformly onto the larger diameter of the molded part. So, it eliminates neat lines which are inevitable with single or multiple point gating, and it reduces potential distortion and prevents core shifting due to one sided loading if dimensions are appropriate. So, the design rule, so the ratio between the core's length and its diameter, so L by D ratio should be less than 1. So, to avoid structural issues. So, so this is what in case of the disc gate, and then tunnel gate we have already discussed. So, tunnel gate these are basically the design principles. So, it is basically connecting the component cavity beneath the parting line. So, this is the arrangement, that is why it is called as submarine gate or tunnel gate. So, it recommends dimensions. So, the taper angle here is around 20 degree to 30 degree, and gate diameter D is equal to S plus 1.5 mm. So, that means the in gate diameter is of course, it is slightly higher than the this diameter of the runner over here, cross section over here. So, this is basically a empirical expression that is used for design purpose, and then this pinpoint gate in 3 platen molds. So, like we have discussed that in case of 3 platen molds, you can see a example kept over here. So, you can see that at one die, I mean one of the die hubs, it is the sprue is kept, and then so this is the, I mean another die hub, it is the runner and ingate, and then another die hub, it is the component which is housed. So, this is useful for very complicated component geometry, where there are multiple cores, and also I mean the cams are running for getting the geometry, I mean different ribs that are present in the component. So, in that case this pinpoint gate is useful, and it requires accurate design for ejection, otherwise it can cause breakage of the ribs that are ribs or undercuts that are I mean kept or created within the, I mean molded component, and the reverse sprue with pinpoint gate. So, I mean so this is a case where, I mean the sprue is basically in spite of a diverging sprue, it is a converging sprue that is being used. So, that is also we have discussed earlier, which is useful for polyethylene and polystyrene. So, this is a special case, and then so we will discuss about ceramic injection molding, but we will do it in the next class. So, we are done with this class. So, thank you for now.